Now we're going to take a look at something that we've actually seen before when we covered transients and time response. Uh, Now we're going to look at it, though, in terms of integrators and differentiators. So in this chapter, we're going to look at um, how we sum, to start with, how we sum the individual instantaneous values, that are created by the charging of a capacitor and create the area under the curve and understand how an integrator works, and then we move to a differentiator. So we're going to look at the operation, we're going to analyze it, we're going to look at what happens with single and repetitive input pulses, and then we'll move on to the differentiator for the RC circuit. So, terms that you need to be familiar with in this chapter: integrator, time constants we've already seen, pulse response, transient time, steady state, differentiator, DC component. So, in terms of time response, a series RC circuit in which the output voltage is taken across the capacitor is known as an integrator. Okay, so when you think integrator, if you haven't had calculus before or a calculus based course, just think in your mind summing everything under the curve. So that's what an integrator does. It's a summing uh, device. Recall that in terms of frequency response, it is also a low pass filter. So you've seen this before as a filter application. Now we're going to look at it to see what happens when we apply a pulse to the circuit and see the integration factor that happens. The term integrator then is derived from the mathematical process of integration or summing, which is a type of circuit that approximates under certain conditions. So, as we learned in chapter 12, a capacitor will charge and discharge following an exponential curve. Its rate of charging and discharging, of course, depends on the RC time constant, a fixed time interval determined by the resistor and the capacitor, and we saw that before as tau. Tau is equal to R times C. So for an ideal pulse, both edges are considered to be instantaneous. Two basic rules of capacitor behavior help us to understand the response of RC circuits to input pulses. The capacitor appears as a short to an instantaneous change in current and as an open to DC. The voltage across the capacitor cannot change instantaneously, and it can change only exponentially. So if we look at integrators and differentiators in their mathematical form, the integrator and the differentiator then refer to functions that are approximated by the circuit under these conditions. For the first one, the integrator, the mathematical integration, then is the averaging process that occurs. The example in this case of the average power, if we look at calculating the power as the area under the curve, we understand that we can only do this for 1/2 cycle, so 1 over pi. We're going to sum everything from 0 to pi, all the values that occur on a sinusoid. So we're going to multiply it, what's in the summing function, by the peak voltage, and we are going to integrate across the angle as the sine of theta and infinitesimal amounts of of the angle. So we're going to move angularly across and do our summations. The opposite of that then is differentiation, the process of establishing an instantaneous rate for a change in quantity. And we saw this with our definition of the current in a capacitor. Okay, so the current in a capacitor, then we look at the change in voltage with respect to time. So what occurs here then, since a capacitor charges when the current starts to flow, is what we're going to look at in understanding the charging and discharging of a capacitor. So when a pulse generator, a square wave generator, we can see that we no longer have the little s, the little sinusoid in here. We've got a pulse. When the pulse generator is connected to the input of an RC integrator, the capacitor will charge and discharge in response to the pulses. So on the leading edge, we've got a transition from 0 to some high or some maximum value. On the trailing edge, we've got the high down to some 0 value. So when the input goes from its low level to its high level, the capacitor charges toward the high level of the pulse through the resistor. But it can't do it instantaneously. It's going to do it as a curve. This changing action is analogous to connecting a battery through a closed switch to the RC circuit. When the pulse goes from high level back to low level, then the capacitor starts to discharge back through the source. Compared to the resistance of a resistor, the resistance of the source is assumed to be negligible. This discharging action then is analogous to replacing the source with a closed switch. So we can see that in the diagram below. We have in A going from high to low, in B or from low to high, in B from high to low. And the explanation here goes through just exactly what we said. But you can see what's happening on the output. The capacitor charging waveform is formed by this exponential curve. The same thing during the discharge. Again, we've seen this before in our DC applications, understanding transients and time constants. So when an RC integrator, the output is the capacitor voltage. The capacitor charges during the time that the pulse is high. If the pulse is at its highest level long enough, the capacitor will fully charge to the voltage amplitude then of the pulse. So you can see here on the input of our pulse, 10 volt pulse at some interval going into the circuit. The output then, we can see what happens as it starts forming the characteristic output, the charging and discharging with that exponential charge and discharge. The capacitor discharges during the time that the pulse is low. If the low time pulses then are long enough, the capacitor will fully discharge to 0. Then when the next pulse occurs, it will start again. So this is, again, characteristic of what we already saw when we looked at time constants in DC. So there's our circuit that we just looked at, and the representation of the output versus the input when we apply a square wave to that capacitor. So for an ideal pulse, both edges are considered to be instantaneous. Two basic rules of capacitor behavior help to understand the pulse response of RC circuits. The capacitor appears as a short to an instantaneous change in current, and as an open to DC. The voltage across the capacitor cannot change instantaneously, but it can only change exponentially. So that's what we've already seen. And again, depending on how long this input pulse is will determine how long it will charge and discharge. Okay, so from the previous section, you have a general idea of how an RC integrator responds to an input pulse. In this section, then, the response to a single pulse is examined in detail. Two conditions of pulse response must be considered. When the input pulse width T sub W, that's the input pulse width, is equal to or greater than 5 time constants, or T sub W, the pulse width, is greater than or equal to 5 time constants. When the input pulse width is less than 5 time constants, then we have our pulse width as T sub W less than 5 time constants. So a capacitor will fully charge if the pulse width is equal to or greater than 5 time constants. So you can see here our width of our pulse. We see that the capacitor is charged up and holding at the input voltage 10 volts. Again, we can see here 5 time constants here is 1 microsecond. 5 time constants here is 2.5 microseconds. 5 time constants here, 5 microseconds, and you can see how the area under the curve is increasing until we reach some point. 5 time constants equal to 10 microseconds. It is maximized, and now we go from high to low, and it starts to discharge. So we can see what's going on with the area under the curve here as we are doing our integration or summing each of these individual, what could be sliced up and considered to be individual pulses under the curve. Okay, so we can see here in this example, in each case 5 time constants, 10 time constants, 20 time constants, 40 time constants. The input versus the output will determine what the wave shape will look like. So when the pulse width is equal to or greater than 5 time constants, we see how the signal input versus output then responds. Capacitors that partially charge, you can see if we don't let it go 5 time constants, that we end up with a pulse that does not reach the input voltage. So 9.5, 8.6, 6.3, and these are all values again that we've seen before based on the time constants. Capacitor voltage for various time constants that are longer than the input pulse width then will have more time to charge. When the time constant is much greater than the input pulse width, the capacitor charges very little, and as a result, the output voltage becomes almost negligible. So again, we can see that from these waveforms. So go back, take a look at these waveforms. Make sure you understand what's going on for the relationship between the input in blue and the output in green based upon how long the capacitor is allowed to charge. That will determine what your output is going to look like. Okay, so the effect then of reducing the input pulse ends up having an output pulse that does not match the input. Okay, so when we come back, we'll take a look at this example here and do some calculations. Again, you've seen these before.